Hey guys, so welcome back to another day of Chem 2. Now at this point, we have kind of touched on briefly alkenes with a double bond, and then alkynes with a triple bond. And so those are all compounds that in some form or fashion contain carbons and hydrogens, just in varying amounts, and the addition of kind of double and triple bonds kind of reduces the amount of hydrogens that are needed per each carbon. And so the time has come for us to kind of introduce two kind of terms of classification that we can use when we're talking about these alkanes, alkenes, and alkynes. And so our learning target today is to be able to classify compounds as either saturated or unsaturated. And then second, to be able to calculate the hydrogen deficiency index for a given molecular formula. And a lot of our notes from today are from chemistrysteps.com, so thanks to them, and make sure to check that link out if you need a little more explanation. So first of all, what I'm going to do is kind of go through and tell you whether or not these 6 example compounds are saturated or unsaturated, and then I'm going to see if you can maybe generate a pattern as to why. So A is unsaturated. A is saturated. Let me get my terms right. B is unsaturated. C is unsaturated. D is saturated. E is also saturated. And then finally, F is unsaturated. So if you'll take some time, kind of right quick, and pause the video and see if you can come up as to a reason why some molecules might be saturated and others might be unsaturated. Okay, so maybe, perchance, one thing that you came up with is that the saturated compounds tend to only have single bonds. And that is the case for A, D, and also E. Those compounds just have single bonds. However, what we see in compound C is it looks like we just have single bonds, but those single bonds are arranged in a ring, okay? And so what we're going to see is that things with multiple bonds, either double or triple bonds, and compounds that have a ring or a cyclical structure are going to be unsaturated. And so what makes them that way? And so what we're looking at is kind of a reference to how many hydrogens they have per their carbon atoms. So if a molecule is saturated, it has the maximum possible number of hydrogens per carbon and other atoms, all right? And so if we take a look, this is butane kind of over here. If we take a look, if you notice, due to kind of all of its single bonds, every carbon kind of has a complete fullness of hydrogens, if you will. And so there's no room to add any more hydrogens. If we did, that would make carbon have 5 bonds, which is a big no-no, since it only needs 4 bonds to fulfill its octet. And so what that means on the flip side, that an unsaturated compound is where the molecule has less than the maximum amount of hydrogen. And so what that means, you could potentially, have or add in more hydrogens per the number of carbon or other atoms. And so we've got 2 examples here. We've got propene, and because of this little double bond right here, what that means is each of those carbons could potentially take on one more bond to hydrogen to give them kind of a full hydrogen bonding set. Now also, we have another molecule here. Because of this double bond to oxygen, this molecule could also take on more hydrogens. One could attach to the carbon and one could bond to the oxygen. And so what we would say about these molecules is they have 1 degree of unsaturation because they could each accept one more hydrogen molecule. The one hydrogen molecule ends up being 2 hydrogen atoms That's because hydrogen is diatomic when it's found as a gas. Okay, so now here's something kind of interesting that falls out when you have unsaturated compounds. Unsaturated compounds are not identical, even though they may have the same number of carbon atoms. So for example, on the left here, this is an unsaturated compound with 3 carbons. And on the right, we also have an unsaturated compound with 3 carbons as well, okay? But here's where the difference is going to come into play. On this first compound, it only has 1 degree of unsaturation due to that double bond. That 1 degree means it has the room to accept 1 more hydrogen molecule. However, the molecule on the right, due to the triple bond, has 2 degrees of unsaturation. So a double bond counts as 1 degree, and a triple bond counts as 2 degrees. And that's because, due to that triple bond, you can potentially add on 4 additional hydrogens or 2 hydrogen molecules in all. And that will generate kind of a saturated alkane. Now, typically, when we're kind of looking at general patterns in alkanes, there's a set formula that the molecules will fit if they are saturated, okay? And so the formula is C subscript N H 2N plus 2. And so what that little n stands for is that stands for the number of carbon atoms. So for example, if we kind of showed you on this saturated alkane here, there are 3 carbon atoms total. And so the way the formula would look is you would have 3 carbons, and then for the hydrogens, it would be 2 times 3 plus 2. And so what that would mean is that if we had a saturated compound, it should have the formula of C3H8. When we take the 2 times 3, that's 6, plus the 2, that gets us to 8. And so what we can do is just by looking at that formula, we can go back up and see, okay, do we have 3 carbons and do we have 8 hydrogens? And if we count, we do end up with 8 hydrogens per those 3 carbons. And so that means we have a saturated compound, okay? So now what we're going to move into is how do we calculate, this degree of unsaturation, which is also termed the hydrogen deficiency index. And the idea is if you're a molecule that's unsaturated, you are lacking or deficient in hydrogen. You could potentially, add on more. And so the way you calculate the degree of unsaturation kind of depends on what information you're given. If you have the molecular structure, you can simply look at it with your eyes and count the degrees of unsaturation. And so essentially what generates a degree of unsaturation is a ring and any bond that's above a single bond. So like a double or a triple bond, okay? So let's just walk through some examples right quick here. So this first one, if you notice, it has no pi bonds. And when we say pi bond, again, that's referring to kind of our every bond above a single bond. So that's what that's referring to. So no pi bonds, no rings. That means it is saturated. It has the maximum amount of hydrogen per those atoms. Now if we go to the second example, this has 1 pi bond, all right, kind of part of that double bond. And so this would have 1 degree of unsaturation. We could potentially add 1 more hydrogen molecule, aka 2 hydrogen atoms, to make this saturated. All right, now let's look at the next one. This one happens to have 2 pi bonds due to its 2 double bonds. So this would have 2 degrees of unsaturation. And when we say like 2 degrees, it's implied that this is, unsaturated. Then finally, this last one is interesting. This one is going to end up with 3 degrees of unsaturation because you have 2 pi bonds and you also have a ring, okay? And let me show you right quick why a ring, ends up being unsaturated even if it has all single bonds. So I'm going to scroll you back up to this original example here of C. And on each of these carbons, they're going to end up having 2 hydrogens. They're just kind of hidden, in the skeletal structure at the moment. Now, what we're going to do is kind of look at our saturation formula, the CnH, 2n plus 2, and see if it fits. So here we would have 1, 2, 3, 4, 5, 6 carbons. So we're at C6. Then let's kind of figure out how many hydrogens we should have if it's saturated. So we have H2 times 6 plus 2. So that means our formula should be, if it's saturated, C6 and then H14. So let's go ahead and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we actually only have 12 hydrogens, all right? And so we see that that ring introduces a degree of unsaturation because C6H12 is 2 hydrogens short of the H14. And so that means we would need to add 1 more H2 molecule. And so that's kind of why rings, even though they may have single bonds, still count as a degree of unsaturation. All right, so now what I'm going to let y'all do is kind of pause the video and give this a try for molecules A through E. So go ahead and hit pause, try this on your own, and then hit play, and we'll go over the answers. All right, so here are the answers right quick. So for A, we have 1 degree of unsaturation. It's a ring. For B, we also have 1 degree of unsaturation due to the pi bond that exists. For C, we have 2 degrees of unsaturation. That's due to the ring plus the pi bond. For D, we're actually going to also have 2 degrees of unsaturation since you have 2 pi bonds that help make up a part of that triple bond. Then finally, this last molecule is benzene. You may recognize him. And he's going to actually have 4 degrees of unsaturation. There are 3 pi bonds and 1 ring. Okay? And let me write this in. Pi bond and ring. Okay. So now, the last thing we're going to look at is what is going to happen when you've only been given the molecular formula without a structural picture of what the molecule actually looks like. So for example, we've been given kind of a big, long, hairy formula here, C6H10Cl NO2. And we're going to try to figure out, okay, well, what do we do if we can't see the molecule and just have a list of the atoms? And so there's a formula that's kind of been put together for kind of good reason. And it's allowing us to calculate the hydrogen deficiency index when we can't see the molecule. And so the way the formula is put together is 1/2. That's kind of everything's going to be multiplied by that. Then you open the parentheses, then it's 2 times the number of carbon atoms plus 2 plus the number of nitrogen atoms minus the number of hydrogen atoms minus X. And X stands in for anything that's a halogen in group 17. So like chlorine, bromine, iodine, fluorine, all those guys. And so let's do it as an example kind of with our compound here. So what we have is we're going to start off our hydrogen deficiency index, aka the degrees of unsaturation, is equal to 1/2 times 2 times your number of carbons, which is 6, plus the number 2, plus your number of nitrogens. In our formula, we just have 1 nitrogen. Then we're going to subtract the number of hydrogens. In our formula, we have 10 hydrogens. Then you also subtract the number of halogens. In our formula, we have just 1 halogen. So we'll subtract -1. And if you'll notice, the oxygen has kind of been ignored, and that's because it normally doesn't affect the degree of unsaturation. So we would do our kind of calculation here. So you do 1/2 times kind of everything that's in your parentheses. So that's 12 plus 2 plus 1 minus 11. And what that gets you is a hydrogen deficiency index of 2. And so that means somewhere within the molecule you have 2 degrees of unsaturation. Maybe you have 2 double bonds, or maybe you have a ring and a double bond, or maybe it's just 1 triple bond. And so if we look at the structure, let me pull my little answer box away here, we can kind of see that the actual structure ends up having 2 double bonds, and those 2 pi bonds are what give us the 2 degrees of unsaturation. And kind of right quick, let me show you just a little bit about kind of like why the formula is put together the way it is. And there's a good article kind of on it that kind of explains the why that you can click on here, but I'm going to try to do it a little short and sweet for you. So when you have a halogen, the reason why you subtract is because halogens tend to take the place of one of your hydrogens, all right? And so if we look at this molecule here that we've kind of been given, if you notice where the chlorine is, he's attached to a carbon. And if he weren't there, that's a space that a hydrogen could occupy. And so the presence of halogens kind of take up one's possible spot for a hydrogen. All right. Now, if you look at nitrogen, all right, that kind of also has an effect on the on the hydrogen count. And why that is because nitrogen, instead of forming typically 4 bonds like carbon, nitrogen typically forms 3 bonds with 1 lone pair. And so you'll notice kind of this nitrogen here, he has 2 bonds to hydrogen, and the other bond is to a carbon that connects him to the rest of the molecule. And so kind of the bonding patterns of the different elements affect the role they play on either kind of increasing the amount of hydrogens or decreasing the amount of hydrogens per a molecule. Okay, so now one more kind of practice opportunity for you. So I'm going to work A with you right quick, and then I'll let you do the other ones and check your answers right quick. So we've got our formula that the hydrogen deficiency index is equal to 1/2 times the 2 times the carbons plus 2 plus nitrogen minus hydrogen minus halogens. So here we have 6 carbons, we have 1 nitrogen, we have 8 hydrogens, and we have 1 halogen due to our bromine. So if we go ahead and plug that in, so that's again 1/2 times everything in your parentheses there. So in your parentheses, you'd have 12 plus 2 plus 1 minus 9 there, and then times 1/2, that gets us 3. So this would be a molecule with 3 degrees of unsaturation. All right, so go ahead and I tell you what, maybe try just B through D. If you feel like you need extra practice, you can try the other ones, but go ahead and pause and try B through D. And the answers are kind of actually right here at the bottom, so you can check as you go along. Then when you finish, kind of press play, and I've got one more thing to kind of tell you. All right, welcome back. So the last thing that you're going to be doing kind of for the practice, your individual practice today, is we're going to apply what we've learned about unsaturation to a topic that's called drawing constitutional isomers. And so what we're going to find is that you can have molecules with the same atoms, but they can sometimes be connected in different ways, all right? And so, for example, you might have 2 molecules like this that each have 1 oxygen and 4 carbons, all right? But sometimes they may be connected, differently just depending on the structure. And what we're going to find is some of the unsaturation can kind of affect, the way the molecules are put together. So what you're going to do is you're going to first click on this link. It's from another site called organicchemistrytutor.com, another kind of helpful, site for OChem. And the article, part of it will be like a review from this lesson, and you're welcome to just skim through that part really quickly. Then what they're going to do is take you through kind of how to apply what we've just learned to draw some of these different forms of a molecule. And so after you read the article, then you're going to be trying these 4 practice problems. And so first, you'll be calculating the degree of unsaturation, or your hydrogen deficiency index for each molecule. Then what you're going to be doing is drawing, 3 different skeletal structures for possibilities for the arrangement of that molecule, right? And so for each of them, for example, for A, you'll draw 3 things. Each of the potential structures should have 4 carbons, 9 hydrogens, and 1 nitrogen. So the number of atoms will be consistent. What will change is just the order in which they're connected, okay? And so then what you'll do after you kind of finish those is you'll check your work with the kind of answers on the back. And so for each answer, there are sometimes more than like 3 possibilities. And so on the answer key, they've just given you kind of 3 of them. And so if your answer doesn't match exactly, and if you're not quite sure, hey, is this really correct? It may be, but you're more than welcome to let me know, and I'll be glad to check it for you. All right, but that's it. So read the article, try the 4 practice problems, and check with your key, and you'll be uploading a picture of your work for the 4 practice problems. All right, thanks so much, guys. Good luck, and let me know if you need anything.